We're going to start our unit on chemical kinetics. Kinetics refers to the rate or speed of a process. And so normally about speed, we think about how fast a runner runs or how fast a car moves. And so in that sense, speed relates to the distance traveled per unit time. Now instead, if we switch our thinking back to our favorite subject, which of course is chemistry, then if we think about chemical kinetics, that's the rate of a chemical reaction. Now I want to explain why this matters, why we care about rates of chemical reactions. Now this statement here, at 1 atmosphere, the conversion of diamond to graphite is spontaneous. And so you can see a diamond with an arrow going to graphite. But we all know that you buy a diamond ring, it doesn't instantly convert into graphite. And so that word spontaneous does not mean instant. It means that the change in free energy is negative. And so eventually, after a long time in this case, diamond will convert back into graphite. So this process is very, very slow. And so the rate of reactions is just as important as whether or not they are spontaneous or non-spontaneous. Another important aspect of kinetics is biochemistry. So the chemical reactions that go on in your body go on at certain rates, and those rates are very important. They need to go on at a speed that will sustain your life. And so the thousands and thousands of reactions that go on in your body are all catalyzed by enzymes, and we will talk about that later in this chapter. But the speed of those reactions is very important to human life, very important to medicine, and so that's another aspect, another example of how important kinetics is. So let's get to what matters here, rate of reactions. We're going to look at this reaction as an example, and then we'll use other reactions later. So we have 3 molecules of hydrogen reacting with 1 molecule of nitrogen to form 2 molecules of ammonia. Here's our reaction. Keep in mind that we have hydrogen and nitrogen on the left. Those are the reactants. And of course we have ammonia on the right. That is our product. If we start with only hydrogen and nitrogen and no product at all in our reaction vessel, and we monitor this reaction over time, one thing that we know will happen is we know that our concentration of reactants should decrease over time because they will be consumed and turn into product. Those brackets, remember, mean concentration, more specifically molarity. We also know that the product concentration should increase over time. And that's going to be the first sort of important piece of information that we talk about. Here's our reaction. 3 molecules of hydrogen react with 1 molecule of nitrogen to form 2 molecules of ammonia. Let's put our reactants in a flask. Here you see only hydrogen and nitrogen in our flask. We're starting with only reactants, no product. Now this reaction will proceed at some rate. Let's say it's a rate that's something like this. Or maybe it's a slower reaction and it proceeds at a rate that's something like this. Or maybe it's a much faster reaction. Extremely quick. Typically what we do when we're talking about kinetics is what we use for rate of reaction is related to the concentration, change in concentration over time of any of the 3 reaction components. And so we're going to look at a graph that measures, that plots concentration versus time for this particular reaction. And I wanted to reiterate that, these are just at any given point in time. Let's take your flask and you let the reaction begin, and then you take a snapshot of it, and then you let it some more. And then you take a snapshot of it again. Proceed some more. And then there's another snapshot. And then each of these snapshots, you could be monitoring any of these three reaction components. And so that's what the x-axis values are going to be, or the time points at which you would take these, quote, snapshots, where you would measure the concentration of any of the three components. Here's our reaction again. We have 3 hydrogen molecules, 1 nitrogen molecule, and 2 ammonia molecules. And we can monitor any of these as a function of time in order to measure the rate of the reaction. And that's the next thing I want to talk about. We're going to have a graph, and we're going to graph concentration as a function of time. But keep in mind the stoichiometry of this reaction. We have 3 molecules of hydrogen and just 1 molecule of nitrogen and 2 molecules of ammonia, because the stoichiometry does affect the rate of change of each of these concentrations. So here we're plotting concentration of hydrogen as a function of time. It starts out at some initial concentration and then it decreases, not linearly, but exponentially. If we, instead of plotting hydrogen, we plot nitrogen, then what we see is that nitrogen also decreases as a function of time. However, the concentration of nitrogen does not decrease as quickly. And that's because there are 3 molecules of hydrogen for every 1 molecule of nitrogen consumed. And so the hydrogen concentration should decrease 3 times faster, because every time 1 mole of nitrogen is lost, 3 moles of hydrogen are lost. Now if we plot the product instead, then what we'll see is that the concentration begins at 0 because we initially start with no product, and it increases over time, again not linearly but exponentially. So we can label those 3 reaction components. And so this is something called related rates. So the rate of change of different reaction components is different. And so the one that we choose to use in order to measure the rate of a reaction is important. The stoichiometry will affect the rate of change. Okay, now we're going to talk about a different reaction. Let's move on from formation of ammonia. This is a reaction that your book uses to introduce kinetics. So we have 2 molecules of dinitrogen pentoxide, and you can see the little ball and stick models of those on the left. And then those 2 molecules will react to form 4 molecules of nitrogen dioxide. You can see those 4 molecules, those models below the formula, plus 1 molecule of oxygen. Now this is a table in your book, table 12.1. And in this particular table, what they're trying to show you is that if they took this reaction, they allowed it to take place, if they, starting with time 0, and every 100 seconds after that, up till 700 seconds, if they took a little snapshot of the reaction in the flask, if they could put on their molecule glasses and count how many molecules they had, and divide that by the volume and determine the concentration, these would be the data points for that experiment. So at time 0, we have only dinitrogen pentoxide, and then none of the products, 0 and 0 in columns 3 and 4. And then if you look at the column for N2O5, you can see that the concentration goes down because it's a reactant. And if you look at the 2 columns on the right for the product concentrations, NO2 and O2 both go up over time. So this is the table I wanted to talk to you about. N2O5, we're going to plot these in the next figure. And before we plot them, I want to show you the plots and what they correspond to. So N2O5 I circled in purple, and I changed the font in the reaction to be purple. And if we plot that one in purple on the next graph, we're going to plot in this teal color, and I changed the font in the reaction. 4NO2 is now sort of this teal aqua color. O2, we're going to make that kind of a royal blue color. So we're going to plot those in the next figure, and that is here. So this is concentration versus time data, just like we did for formation of ammonia, but it's just a different reaction. And you can see the purple is our reactant. It decreases from 0.02 molar. It decreases over time. And then we also have both of our products. One is kind of an aqua green and the other one is blue, and those both increase in concentration over time. As we discussed before, the concentration of NO2 that you see in that teal color, that increases 4 times faster than the concentration of oxygen, which you see in blue. And that should make sense because 4 molecules of NO2 are formed for every 1 molecule of O2. So it should increase 4 times faster. Now, next thing I want to talk about, I'm adding in that's just words about what I just told you. Now I'm going to add in this last image before we go on and talk more about this. We're going to talk about what is the difference between an average rate and an instantaneous rate and an initial rate. So they're all rates. They're all change in concentration over change in time, but there are different ways of measuring them, and that's the next thing I want to talk about. Here we have concentration of NO2 as a function of time. Remember that NO2 is increasing over time. This is a product. We're going to use this as an example to compare average rate, instantaneous rate, and initial rate. So the average rate is related to time points on the graph. And so there are specific time points chosen. In this case, we have 200 seconds and 300 seconds. These could be chosen on the graph, or they could be in a table like the one that's provided in the book for this particular reaction. And the average rate is simply the change in concentration, so the final concentration minus the initial concentration, divided by the change in time, which would be 300 seconds minus 200 seconds, which would be 100 seconds in this particular example. So this could be used from data in a table or from the graph. Now, instantaneous rate is a little bit different. Here I have drawn a line that is the tangent at t equal 300 seconds. So you can see I put a dot there at 300 seconds, and I drew the tangent line which touches my particular graph line at the 300 second point, but it's a straight line, so it only touches at that one point. So this is called an instantaneous rate because it is only at one time point on the graph. We're only talking about 300 seconds. If it were 200 seconds or 205 seconds or 306 seconds, it would be slightly different because we would have to choose a different point on our graph. So we draw a line that is tangent to that curve at 300. If we take the slope of that tangent line, then that would be the instantaneous rate at 300 seconds. Now you can have an instantaneous rate at any time point. You can choose whichever time point you want. But the slope of the tangent line at t equal 300 seconds is the instantaneous rate. And you can see there I've got the orange dashed lines to show you that I'm doing change in y over change in x. That's the slope of the red line. The slope of that line is the instantaneous rate. Now, I want to talk about instantaneous rate, and I want to look at the 300 second tangent line, and I want to compare that to, here we have the 200 second tangent, and then there's the 400 second tangent and 500 seconds. And what I want to know is, and there's 600 seconds. So the point of this is that my tangent line, the slope of that line is changing as the reaction proceeds. It seems pretty clear, and let me know if this isn't clear to you, that the slope decreases as a function of time, which means that the instantaneous rate decreases over time. As the reaction proceeds, the rate goes down. And this is important This is important because we are going to use what's called an initial rate. An initial rate is the instantaneous rate at t equals 0. And this is almost always the rate that is used in reactions. Whenever you see the rate of this reaction is this, it is almost always, without exception, the initial rate. The reason we use the initial rate, which is the instantaneous rate at t equals 0, so it's the slope of the line at the tangent line at t equals 0. The reason we do that is because the other ones change over time, and this one would be a maximum rate. So this figure is meant to show you a comparison of the average rate, which you can see here is just simply change in y over change in x. It's just those two data points. And of course the instantaneous rate, which is the slope of a tangent line drawn at any point on the graph. And the initial rate, which is basically the instantaneous rate at t equals 0.